Hey everyone, I'm Oyewale Ayobami Owode with matric number EG 2019-074. We'll be taking you on image compression today, which we did for our project. And with me here are my group members.
Hello everyone, my name is Babalola Tosin Moses and my matric number is EG 2019-029.
And I'm Ola Kenijesu with matric number EG 2019-011.
We'll be diving into the fascinating world of image compression, where you would see how we use discrete cosine transformation, which is DCT, to help us compress images while retaining the visual quality. Before we begin, I would like to explain what DCT entails. DCT is a widely used technique in image compression. It is a mathematical transformation that converts a spatial domain image into a frequency domain representation. The main goal of DCT is image compression and is to reduce the redundancy in the image data and retain only the essential information needed for good visual representation. The DCT transformation breaks down the image into small square blocks and flattens each block by using the DCT formula and compression ratio divided by the user. I would like Akin to give us a perspective on image compression as a whole. So I will let them take it from here.
Yeah, thank you very much. When it comes to dealing with digital images, especially high resolution ones, the file sizes can get pretty hefty. Uploading and storing these files can be a real challenge. That's where image compression comes to the rescue. Image compression is a technique that allows us to reduce the file size of an image without significantly affecting the visual quality of the image. The degree of data loss can be controlled by adjusting the compression settings, as will be explained as we go on in the video. I'll step back for a moment and let Mr. Tosin let you know how to get the path file for your image.
Yeah, thank you for that. From the attached code placed in the link below, you will notice that you will have to surgically pick out the file path from the laptop yourself. No worry, I will show you how you can do that shortly. Go to your file explorer, then right click on the image you want to choose. Then go to the property, click on it. Then copy the file location and go back to your code. Then paste it at the file image location. Go back to the file explorer. Copy the image name. Then go back to the code and paste it at the image name. Then go back to your file explorer again. Copy the image format. Then go back to your code. Paste it at the image format. The last information needed is the format of the image, which you see type of the image. Also note that while converting your image, converting from one format to another may increase or decrease the size said compressing image. I'll pass the mic to Ayo for input on how the code actually works.
Alright, thank you Tosin and Akin for that good explanation. Alright, let's break down the code step by step. First, we read an image from a specific path file which Tosin has already taught you guys on how to do. Then on my own laptop, that's on our laptop, using the imread function, that's what we use to read the file. We chose an image of this stunning image, human eye. So we chose it's an eye resoluting image. That's how we used it. Then next, we check if the image is of color or grayscale. That's what this code is meant for. It converts the images back to grayscale if they are colored images. That's how in RGB format. Now for this demonstration, we'll convert the image to grayscale using the RGB2 gray, which is this function. Yeah. If it's in color, that's for the image. The reason we had to convert to grayscale was because using the image is of colored. Using the image in its colored form takes up a lot of data, which we don't want to give the MATLAB to work on. Now that we have the image, we'll convert it to a double precision. This is essential for accurate calculation using the compression process. The next step is where the magic happens. We perform the discrete cosine transformation on the block of an image using the block bulk, which is this. And the block size here determines the size of the DCT block we'll be using. And we set it to a block size of what? Of 8. Yeah. These numbers, when being adjusted, affects the amount of compressed data from the image at every given point.
The block size at which we set the image to break up the set image into pixels is 8 here, which means it's a 8 by 8 pixels cutting we're making it to do. If it was a block size of 6, it would have been 6 by 6. Now we set the threshold for the compression. Now the variable compression determines the compression level. It specifies how many percent of the DCT coefficients are kept. For example, a compression of 40% means that only 40% of the DCT coefficients will be retained. Now we're using a 50% DCT coefficient here. That's why we set our compression ratio to 50. Now, to determine the number of coefficients to keep, we round up the coefficient number. If these are imputed 48, it will be rounded up to 50 at that point. So producing an image of compression ratio 48 and 50 are the same thing. Now I'm going to go to the compression function down below in the code to explain. Now the function compress DCT is called to perform the compression on each block of the DCT image. The compression DCT function keeps the top coefficients to keep coefficients and sets the rest to 0. This step effectively discards less important frequency components in each block, achieving compression. Yeah. Now, performing inverse DCT on compressed image blocks. After compression, the IDCT2 function, that's this function here. What is it? Is used to perform the inverse DCT on each compressed block. This reconstructs the compressed images with reduced quality due to lossy compression. We are carrying out lossy compressions in our code here. So after breaking up the codes into 8 blocks, that's 8 by 8 blocks, it assembles them right after compression, then produces it as a compressed image. Now, after converting the image, the reconstructed compressed image is converted back to the UINT8 format using the UINT8 function. This step ensures that the pixel values are represented in the range of 0 to 25. This function does that. Now, the original and the compressed images are displayed side by side using the subplots. The subplots help us to visualize our images as a figure. An IMShow function allowing us to visualize comparison between the two. Now, this extra code, which is placed here to convert the compressed image to colored function, was added due to us initially converting the image from a colored version. That's if the image imputed was a colored version of itself to grayscale, which is black and white. So we have to convert it back to its colored version, that's RGB, using this function, the IND to RGB. So this function does that. So now let's run the code. I think they made a mistake. care of putting two dots. So copy the file path which Tosin had initially demonstrated to you guys on how to get. Then we'll paste it here again, same function. So we'll run our code. This is the image we're trying to actually get a compressed version of. Hopefully we perform a lossy compression. Our figure is here. So like I previously said, it creates a grayscale of the original image and imputes it into the MATLAB, then converts it into 8 blocks and reassembles them after compression as an image. And this is the compressed image here, so we just have to download, save the file. Let's save it as 254 image human eye. Then the format at which we want to save it at is JPEG, because that's the format at which it was given to us at first. Then we'll save. Then we'll go to our documents and see where it's located. Is it 132 KB? This is the initial image, which is of 204 KB, so down to 132 KB. Now comparing both images side by side shows you there isn't really much difference in it. Actually, you can, depending on how you want it to compress, if you want the file size to be reduced, all you just have to do is increase the block size and also increase the compression ratio, and there you have it, fully compressed. So I'll be passing it on to Tosin again to give you a little bit of comprehensive view of image compression if necessary.
Thank you, Ewan. Thank you, Ayo. He has, explained the code to us. So there you have it. A comprehensive view of image compression. Image compression using DCT is a powerful technique to reduce file size while maintaining acceptable level of visual quality. You can experiment with different compression ratio values to find the right balance for your specific needs. Whether you're a professional photographer, a graphic designer, or simply someone who loves sharing image online, understanding image compression can significantly impact how you handle your visuals. If you find this video helpful, don't forget to like and share with your friends. If you have any question or want to share your thoughts, leave a comment down below. Thanks for watching.